In today's talk, I'm going to talk about dexterous robotic foundation models. So the starting point for robotic foundation models is vision language action models, or VLAs. VLAs are based off of multimodal language models, or vision language models. So the idea is that we start with a large language model that can already understand a lot of semantics, and then we further train it to be able to process images by embedding images into the same embedding space as language. And then we further adapt it for robotic control. Now, the earliest VLAs, like the RT2 model illustrated here, framed robotic control essentially as a kind of a question-answering problem, where the question was the instruction to the robot, and the answer was a sequence of numbers representing the actions that the robot should take to carry out that instruction. Of course, to train robotic foundation models, it's not enough to just design the model. You also have to obtain the data set. And one of the big innovations to enable robotic foundation models to be practical was what's called today cross-embodiment training. One of the more significant works in this area was RTX. In RTX, the idea was to collect data from many different robots by essentially just asking researchers to donate their data to science. So the RTX dataset consisted of data from 34 different research labs, containing 22 different kinds of robots, lots of different skills. I can go into the statistics of this in a lot more detail, but it's perhaps easiest if I simply show some videos of the different types of situations seen in RTX. So you can see that there's a lot of diversity. All the robots in this case are single-arm parallel draw manipulators, but they're doing lots of different things from different viewpoints and so on. Now, even though the RT2 model was fairly straightforward, it only produced discretized actions framing it as essentially question answering, and the RTX dataset was limited because it only had single-arm platforms, there were still a lot of pretty interesting initial results that could be shown even back then. So one fun experiment was to take a model trained on the entire RTX dataset and then ask the different research labs that contributed that data to test the model on their particular tasks. So you can see some of the test tasks on the slide, and there's a lot of variety here, from moving objects to routing cables to opening drawers and containers. And here are the results. So for each group, this is showing the particular tasks in each lab. So each lab was asked to test the model on whatever tasks they were developing, that they were working on. The rainbow-colored bar is a model trained on the entire RTX dataset, so the cross-embodiment model. The colored bar on the left side is whatever model that lab had developed for their own tasks. So this is a specialized model. And the middle bar is a baseline. And what you can see in the averages plot on the right, where it says mean, is that the cross-embodiment model, the rainbow-colored bar, is about 50% better on average than either the baseline or the specialized models that each of these labs had. And that's actually really, really interesting, because each lab had a different method that worked well for their particular tasks, and here comes along this cross-embodiment generalist model that actually beats all of them by a pretty large margin. That's pretty exciting because it kind of shows the beginnings of what we saw with LLMs, where it used to be that people would develop specialized systems for machine translation and text summarization, other NLP applications, and then along came these generalist LLMs that could outperform all of them by being more general and by leveraging more general data. And here we see the beginnings of that in robotics. And of course, these kinds of models could do some pretty cool tasks. They could follow language instructions, understand basic spatial relationships, understand semantics. The version of the RT2 model trained on a cross-embodiment dataset did about 3 times better on difficult generalization tasks than the original RT2 model that was trained on only this robot. So that's pretty interesting, because that's showing that the performance of this robot is actually improved on the hardest task by 3x just from including data from other robots. So this was all really interesting, and this kicked off a lot of excitement about robotic foundation models and VLAs, but just from watching these videos, maybe some of the limitations of these kinds of approaches are becoming apparent. So where does all this get us? Well, what we had at the time was a kind of a first-generation VLA, where the robotic control problem was framed as a question-answering problem. These models were able to inherit internet-scale knowledge to improve robots, and they gave us a hint about how to bridge the data gap by aggregating data from many different robot types. But of course, there were a lot of things that were still lacking. The tasks were really, really simple, and generalization and language following was still pretty limited. So it was pretty exciting that there was some non-trivial knowledge transfer from pre-training, but it was also clear that this knowledge transfer only got us so far. And of course, the design of the model itself was not adapted to the particular demands of robotics. It was simply outputting text that represented actions. So from there, it really made a lot of sense to look at how to adapt VLAs specifically to the demands of dexterous control, and simply framing control as question answering wouldn't cut it. And it was also important to think about post-training methods that could enable better performance and better dexterity, and perhaps also better robustness. And that's what I'm going to talk about in today's talk. So I'll start by introducing what I would call a second-generation vision language action model. Second-generation VLAs at this point are about a year old, and to explain what second-generation VLAs are, I think I should first tell you about how LLMs turn into VLMs and how VLMs turn into VLAs. So a large language model is a transformer that uses self-attention, and it has a causal self-attention mask that allows it to autoregressively decode text. And this is also what enables us to train LLMs with next token prediction. So in a training example, you get the prefix and then you predict future tokens in text. Now, if you want to take these LLMs and adapt them so that they can also understand images, what you have to do is basically embed images into the same representation as the text. So there are a few different recipes for doing this, but one of the most common is to take images, encode them with some kind of image encoder, and then use a little embedding layer to essentially map those image tokens into the same embedding space as the language tokens. Essentially, it turns the images into a language-like representation that the downstream LLM can process. And of course, if you train this end-to-end, then the LLM actually adapts its internal representation to be more suitable for both text and images. And we can use this for things like visual question answering. So the first generation VLAs essentially used exactly this approach to control robots by simply framing robotic control as a kind of question answering problem where the suffix, the answer, was replaced with a sequence of numbers. In a second generation VLA, what we're going to do is we're going to add an additional neural module that is specifically designed for control. Control is continuous, and if you want dexterous control, then it needs to also be high frequency. So you need a portion of the system that is specialized for processing continuous high-frequency actions and, in general, continuous information in the same way that the VLM has a specialized component, the image encoder, for processing images. That makes sense. Like you can sort of think of the language model as a little brain, and then the image encoder is like its visual cortex. So now if you want to also do motor control, you want to graft like a little motor cortex to it. And because actions are continuous, it really helps to represent the distribution over actions with a very powerful continuous density model like diffusion or flow matching. So second generation VLAs add some additional neural module, which typically uses diffusion or flow matching to represent continuous actions, typically actually action chunks. So an action chunk is a short sequence of actions, and that really helps to capture complex, fluid, and dexterous behaviors. There are a few ways of doing it, but one good design, which is probably the most popular at this point, was introduced in the Pi0 model. And in the Pi0 model, you can think of it as essentially a kind of mixture of experts design, where the action expert is also a transformer, and it can attend to all the activations inside the large language model, but it has its own set of weights, which allows it to specialize for motor control, and it's trained with a different loss, which is flow matching. You could also use diffusion, which is very similar. But because it is also a transformer that attends to everything in the large language model, it benefits from the rich representations in the LLM, and mechanically it can be implemented very much like a mixture of experts, except in a traditional mixture of experts, which expert you use for each token is determined by some kind of router, whereas here it's hard-coded, where you would use the LLM as the expert for any language components and the action expert for any action tokens. So essentially, second-generation VLAs add a dedicated continuous output mechanism that can specialize for motor control, like a virtual motor cortex. So here's a summary of the Pi0 second-generation VLAs, which introduced this kind of design. And in Pi0, it used a small VLM called PolyGemma, based on the Gemma LLM, and an action expert with about 300 million parameters. The action expert is also responsible for processing all the continuous information, like the robot's joint angles. So this model took as input between 1 and 3 images, depending on the embodiment. a language command, an action expert that could attend to all the internal values of the VLM, joint angles, and it was trained to produce an action chunk of 50 time steps with flow matching. Now, of course, to make a model like this work, we don't just need the right architecture, we also need the right data set. And the other thing that the Pi0 model made use of is a more advanced training recipe that better mirrored the kinds of recipes that have been successful for other foundation models, namely a pre-training, post-training recipe. So the pre-training dataset for Pi0 consisted of a very large dataset of about 10,000 hours of data for many different robots, as well as, of course, internet-scale pre-training for vision language processing and all the prior open-source robotics datasets like RTX. Now, this pre-training dataset was very large, but it was not of very high quality, so it had a wide variety of different behaviors, some which were done well, some which were done less well. So to get the model to perform really well on downstream tasks, Pi0 used a post-training stage with a smaller amount of data that allowed it to specialize to a particular task. Now, oftentimes, using a combination of pre-training and post-training was actually beneficial even when the post-training data was present in pre-training. So the right way to think about post-training is that it's not changing what the model what task the model is solving necessarily, but rather it's telling the model how it should do the task. This is very much an analogy to LLMs. Like with LLMs, most of the knowledge that they have is actually gained from the pre-training phase. And then the post-training phase serves to tell the model how to use that knowledge to actually solve tasks. So in the same way, the post-training phase for Pi0 tells it, like, these are good strategies for laundry folding. This is what you should actually do, but the pre-training is still useful. So the reason for this is that the post-training data is quite narrow. It illustrates consistent strategies to perform the task well, and because those strategies are very consistent, they don't have a lot of variability in the kinds of mistakes that you see. So by itself, this doesn't work. The robot gets confused if it makes a mistake. But when you combine it with pre-training, the pre-training data illustrates many different situations, and seeing all those different situations allows the robot to understand what to do when something unusual happens. So you really need both the pre-training and the post-training stage. And if you can combine them, then you can get really good performance. You could also fine-tune to novel tasks that were not seen in pre-training. So here's a task where the robot has to take a flattened box and assemble it. And here you could see Suraj throws the box in front of the robot, and the robot gets to work. And the robot puts together this box, and this is a very difficult task because you can see that in many cases it messes up, like there it missed the grasp and it needs to try again. But because the model has been pre-trained and sees all these different edge cases, it actually can recover from those mistakes and build the box. And this is a hard task, so it requires the robot to brace the box against the table and perform very delicate manipulations. The task works successfully, and it works successfully across many trials in a variety of different initial positions of the box. Now, of course, what we care about in terms of the science is to understand, does it actually matter that the model is pre-trained? So here, the solid colored bar is the full recipe that has the pre-training and the post-training. The dashed black bar is a version where we use only the post-training data. And then the bar that you can barely see, which is at 0 for all these tasks, is 0 shot. So that's basically pre-training without post-training. And you can see that the full model is 2 times better than the baselines for building the box, and quite a bit better for some of these other tasks. Of course, on some tasks, the pre-training doesn't make as much of a difference, but in many cases, it makes a really, really big difference. And these are new tasks that were not seen in pre-training, so it's kind of the hardest case for using pre-trained models. And of course, we can use this model to solve pretty complex tasks. So this is a laundry folding task where the robot needs to take laundry items out of the basket and fold them. And this actually works very well. The model is pretty robust. It can fold a variety of different clothing items. And again, this task is really difficult because the clothing item might be in all sorts of initial configurations when it's in the bin. Here you can see more videos. There you can see a different robot doing it. And you can see it's not perfect. It sometimes makes mistakes, but eventually it recovers from those mistakes and does the task successfully. Here at the bottom now you can see the robot is doing another laundry task where it's actually taking laundry out of the dryer, and then it can go and fold it. One of the interesting things that we found with these models, which was kind of an emergent property that we didn't expect, is that they're surprisingly robust. So here, Michael is going to mess with the robot. He's going to put actually another item on the table, and that's going to cause the robot some trouble. It's going to struggle to fold the shorts when there's this other item getting in the way. And eventually it figures out this is a problem and just puts it back. And this behavior was not intended. It actually came through from training on lots of data, but it actually works pretty consistently. And here in these videos, you'll see all sorts of other perturbations where Michael will go in and mess with the robot in various ways, and in all these cases, the robot has reasonable recoveries and reacts intelligently. And that's because it has this pre-training, post-training recipe where the pre-training data illustrates a broad range of situations that might never be encountered by a good strategy. And of course, you can put all this together and actually get an end-to-end policy that performs a pretty complex long-horizon task. So what you're seeing here is a single policy running continuously. There's no hard-coded switching or planning, and it gets the laundry from the dryer and then folds it. And again, it's far from perfect, so it'll often have misgrasps or mistakes, but it recovers from those mistakes, and that's what allows it to succeed. Now, there have been quite a few papers published about all sorts of different VLAs, and what we're seeing pretty consistently across the range of VLA papers that have been coming out is that this second-generation recipe, where there's a dedicated neural module that is responsible for continuous actions, is actually probably the most popular recipe. And oftentimes that's done with a separate action expert, sometimes with a separate action head, but across the board, pretty much all of the state-of-the-art VLAs today use this kind of second-generation recipe. And of course, the Pi0 VLA itself is actually a pretty strong baseline. So even more recent research often compares to Pi0, and we see this kind of generalist model doing very well, even head-to-head comparisons in research papers that are proposing newer designs. So what are some takeaways from this? Well, we have a prototype of a generalist model trained on many robots. It's a VLA recipe that is suitable for dexterity and for fluent robotic control, because now it can represent these high-dimensional continuous action distributions, and it gets excellent performance across a range of extremely complex tasks. But there are, of course, still limitations. It's trained via imitation learning, not optimized for task success, robustness, or speed, so there's still room for improvement. And there's a lot more that we could do. So one of the things that I want to talk about in the next section of the talk, which is a little bit more forward-looking, is how reinforcement learning could enable even more dexterous skills, and a few initial thoughts about how that can go together with robotic foundation models. And I'll emphasize that at this stage I'm talking about things that are really at the bleeding edge of current research. So these are not things that have been fully integrated yet, and not necessarily a case where we have a complete model like Pi0 that has all those components, but we can talk about the ingredients, and that can give us a really strong sense for where to go for future research. So to think about how things like RL can fit into robotic foundation models, let's think by analogy to foundation models in other areas like LLMs. If you want to train an LLM, you first pre-train it on data that you scrape from the web. And then you have a post-training phase, but the post-training phase doesn't just use supervised learning like we did in Pi0. It might also use reinforcement learning like RLHF or RL from verifier feedback to get the model to be better than what it could do using just human supervision. And that's a really powerful idea, and it can be even more powerful in robotics, because while humans are pretty good at answering questions or producing code, humans might not be as good at teleoperating robots. So if the robot learns itself how to perform the task more optimally for its embodiment, it can be much more powerful than what it could learn with supervised post-training. So a possible future recipe for robotic foundation models might involve pre-training on this diverse data, but then fine-tuning with some SFT, some instruction fine-tuning, and also some automated RL to make it even more proficient. So let's talk about the state-of-the-art of RL algorithms for robots. Here's a video of a current RL algorithm learning a chip insertion task into a PCB board, and it's learning this from images. Now, conventionally, we often think that RL from image pixels is very inefficient. So if you look at kind of older papers for learning Atari games, you'll see that sometimes it might take hours, maybe even days of data to learn how to do a task. This policy is actually trained in about 15 minutes, so you can see in front of your eyes there's a timer, and it already learned how to insert the chip occasionally. After about 15 to 20 minutes, it does it consistently at 100% success rate, and you can actually perturb the robot and it will still recover. The same algorithm could be used to learn other skills like routing cables, and here again you can see that this method is actually fairly robust to perturbations where we can move the clip out of the way, and the robot actually follows it around and inserts the cable. Now, we compared this method to imitation learning. This is a method called SERL, which actually has an open source implementation. And here, to make it fair, we gave the behavior cloning baseline, shown in blue, the same amount of data as RL. So RL collected its own data autonomously, whereas the BC baseline was given additional demonstrations up to the same total amount of data. This is showing the success rate, and you can see that here the RL method has 100% success across these three tasks, whereas imitation learning is quite a bit worse. But even more importantly, we could look at cycle time, meaning how many seconds does it take to complete the task. And here you can see that RL is 2 to 3 times faster than imitation learning because it's actually optimized to do the task better instead of relying on imitation. Now, how does this method work? Well, in terms of the actual core algorithm, it's not actually particularly exciting. It's actually using foundations that have been known for a while, but are just implemented in the right way. So the core algorithm is something called RLPD, which is a variant of soft actor critic that uses prior data, so it incorporates some demonstrations to get started. So it's an off-policy actor critic initialized from demonstrations. The observations are images, and they use a wrist camera and a pre-trained vision encoder. So in many ways, borrowing some of these ideas from robotic foundation models, but in a much more specialized setting. The reward is actually sparse. It's just given by an image classifier that looks at the final image and gives it a 0 or 1 depending on whether it succeeded. So this is a fairly realistic case. There's no manual reward shaping, but there are some demonstrations that are provided to get it started. Optionally, for very difficult tasks, we can also actually incorporate human interventions into the learning process, which you can think of like a coach. So the human will intervene when the robot makes a mistake and show it how it could do it better. And that really helps with exploration. Eventually, the robot might actually do the task better than the human, but in the course of learning, those interventions can really help. So you can see here in blue, the policy is running autonomously. And in red, there's a person that intervenes and actually corrects a mistake that the policy made, and then switches back to blue so that the policy can keep going. And this can really help speed up training because in the early stages, the policy makes lots of mistakes, and it's much more efficient for the human to coach it how to get out of those mistakes rather than waiting for the policy to figure it out on its own. So combining these ideas, we can get human-in-the-loop SERL, which is actually a very powerful method. So here you can see this method with human-in-the-loop interventions training for a dashboard assembly task. This is a pretty difficult task because the robot needs to line up all the pins in the dashboard and insert it correctly so that it can succeed at the task. And it requires controlling both arms. After training is done, it can insert the dashboard successfully pretty much every time. So you can see here in the close-up how it lines up the pins. Here are a variety of other tasks learned with this method. Now, this is not a robotic foundation model yet, so each of these videos you're seeing is a different policy, but they each illustrate different phenomena. So in the top left, you can see deformable objects with a timing belt. In the top right, you can see IKEA furniture assembly, where it actually has to line up all the pins. Now, here Charles still needs to go in and screw in the screws on his own, but the robot will move all the pieces. In the bottom left, you can see a dynamic task, which is flipping an egg. And in the lower right, it's using a whip to remove a Jenga block. And there's no trick here, like the blocks aren't glued together, it really is doing this for real. And when you train with RL like this, you also get a policy that's pretty robust to perturbations. So here Charles can go in and mess with the robot and will actually recover and still try to put on the timing belt. So the point here is that RL can give us these very proficient specialists that are really good at individual tasks. And if we build on this, then perhaps we can do a good job of training even more proficient robotic foundation models that exceed the performance of human supervision. But there's a significant technical challenge in adapting these RL methods for robotic foundation models, because training an entire giant model with RL end-to-end in real time is both difficult from an algorithmic stability standpoint and computationally very intensive. So there are a few different ways that people have approached this problem to combine these specialist RL algorithms with robotic foundation models. One method that I'll describe it was proposed in this paper called RLDG, led by Charles Shu. The idea in RLDG was essentially to use RL as a data generation mechanism. So here we would take some demonstrations, which could be provided by a person, or they could even be initial attempts at the task by the foundation model itself, and use them to bootstrap a much smaller model that tries to solve the task with RL. Now, that smaller model doesn't benefit from the representations inside the robotic foundation model, but it can produce training data. And that training data is actually really, really good data for then training better robotic foundation models. So one of the interesting things we found in this paper is that actually using data from RL experts actually leads to better robotic foundation models than using human demonstration data, even if the success rate in the data is exactly the same. And it actually kind of makes sense because the RL experts are Markovian policies that are solving the task using the sensors actually available to the robot. So they kind of on an even playing field, and therefore the data is more suitable for training the downstream foundation model. So to illustrate a case of how this could work, we could use RL to train specialist policies maybe for inserting 3 different kinds of connectors, like a VGA connector, a USB connector, and something else. Now, those specialists are really good at the connectors they're trained on, but they don't generalize broadly. So what we can then do is take the data from these specialists and use it as training data for a robotic foundation model, in this case OpenVLA, and that foundation model will then generalize to new connectors. So the job of the foundation model is to look at the strategy learned through RL and generalize it more broadly. So that's a pretty effective strategy to get foundation models that benefit from RL. Now, of course, it's not a perfect strategy because we still don't benefit as much from the representations in the foundation model. The training processes are separated. So can we actually run RL on top of VLAs directly? And this is a newer method developed by Andrew Wagenmacher and his collaborators called DSRL, diffusion steering with RL. So the idea is this. Second generation VLAs typically use diffusion or flow matching, which essentially maps samples of noise, random noise, to actions. So diffusion models take noise and they convert that noise into reasonable actions with that have a high probability into the data. So what if we do RL, but instead of doing RL in the space of actions, we do RL in the space of noise samples that are sent into the diffusion model? So after RL training, we'll still run exactly the same diffusion model, but instead of giving it random noise, like noise from a zero mean univariance Gaussian, we'll give it specially selected noise, and it's the selection of that noise that is trained with RL. It's almost like soft prompt optimization. And the key here is that now we're benefiting from all that intelligence in the VLA, so the RL actor that outputs that noise doesn't have to be very smart. In fact, even if it outputs completely random noise, it's going to be as good as the original VLA, and if it makes that noise just a little bit smarter, it's going to immediately get better. So the actor and critic in the noise space can be much smaller and much weaker, and critically can learn much, much faster. So here's an illustration of this DSRL algorithm running in the bridge data setup. First, you can see the performance of the original VLA. So it succeeds 3 times out of 8 on this task that requires putting the mushroom on the towel. So it's a pretty small scale experiment. And now we're going to run DSRL. This method is so efficient that the rewards are actually assigned directly by a person pushing a button. It takes only 50 episodes to learn this task. So if I fast forward, you can see the graph in the lower right. It's basically 1 or 0. So the blue dots represent each dot represents 1 episode, and if it's 1, that episode succeeded, and if it's 0, it failed. And we can keep progressing, and you can see that as it progresses, the frequency of successes gets higher and higher. So it's really learning right before your eyes, and all it's doing is changing the noise that goes into that diffusion model. So that's really nice, because then you're benefiting a lot from this pre-trained robotic foundation model. It's improving exploration. It's also providing a degree of safety, because it's extremely unlikely to take very bad actions. DSRL is also just a very good RL algorithm in general, even on benchmark tasks, non-robotic benchmarks. It's a very fast online RL algorithm, and it's also going to match state-of-the-art offline RL methods, so it's very versatile. So that makes it a really good choice to get started on training robotic foundation models. Okay, so to conclude in terms of takeaways, what we have so far is some very efficient RL algorithms, a way to distill RL skills into VLAs, and a way to augment RL with knowledge from VLAs with something like DSRL. But I think that this area is not yet finished. We still need a stable, effective end-to-end method for VLA plus RL. So all the methods I showed, they all train some smaller network with RL. They don't train the whole VLA. So that's something that still hasn't been fully nailed down. And I think there's a lot more that we could do to boost exploration with VLAs, because VLAs have a very rich understanding of semantics, so when given a new task, they should be able to work through that task by using that semantic understanding. And that's a topic for future research. All right, thank you very much, and I'll end there.